At Space Launch Complex 41, an Atlas V rocket is fueled and ready to launch the 5th Space-Based Infrared System satellite for the United States Space Force. Good afternoon and welcome to Cape Canaveral Space Force Station in Florida. I'm Dylan Rice, Systems Test Engineer, Launch Conductor, and the host of this afternoon's broadcast. Liftoff is set for 1:31 p.m. and we have a 40-minute launch window for today's launch attempt. A few seconds from now, the count will enter a planned 15-minute hold. We have 2 planned holds in our 7.5-hour launch count today. These holds give our team additional time to resolve any issues prior to entering terminal count. However, at this time, the team is not working any issues and we are proceeding towards an on-time liftoff. Early in today's show, we'll hear from Systems Engineer Tim Pika about getting today's mission ready for flight. Then stay tuned after liftoff to follow mission events leading to spacecraft separation and to learn more about the SBIRS GEO 5 satellite from a recent conversation I had with Lockheed Martin's Melanie Young. And Lieutenant Bryce Leader and Lieutenant Adam Farrell will join me here in the ASOC to talk more about this mission and the important work done by the SBIRS constellation of satellites. In addition to watching our webcast, you can also follow live mission progress at ulalaunch.com. Jessica Williams, weather officer for Space Launch Delta 45, recently briefed the team. Here are the numbers. The probability of violating launch constraints is less than 10%. Ground winds are 17 to 22 knots out of the east, and the temperature is 80 degrees Fahrenheit. With that forecast, the weather is within launch commit criteria and looks favorable for our planned T0 of 1:31 p.m. Eastern Time. Today's flight will fly an easterly heading away from Cape Canaveral. In addition to the 5th SBIRS satellite, today's flight also includes 2 multi-manifest satellites. Let's take a look at what else we can expect to see.
5, 4, 3, 2. We have RD-180 ignition and we have liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine and 2 solid rocket boosters ignite to generate more than 1.5 million pounds, or nearly 6.7 million newtons of thrust to lift the rocket on its way towards a geosynchronous transfer orbit. Shortly after liftoff, Atlas begins a pitchover to attain the proper flight path, while minimizing the dynamic pressure the vehicle experiences during flight. The Atlas V reaches Mach 1, the speed of sound, at 47 seconds. Following burnout, the 2 SRBs are jettisoned at 2 minutes 9 seconds to shed their weight. Within the next 2 minutes of first stage flight, the Atlas V rocket will more than triple its velocity. Approaching booster engine cutoff, the Atlas V is burning propellant at a rate of 700 pounds, or 320 kilograms per second. With propellant levels depleted, the booster engine shuts down at 4 minutes 10 seconds, having reached space. The Atlas V is now traveling nearly 12,500 miles, or 20,000 kilometers per hour, located 73 miles, or 118 kilometers in altitude, and 235 miles, or 378 kilometers downrange. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs a little more than 7% of what it did at liftoff. 10 seconds later, Centaur's RL-10C11 main engine ignites for the first burn. Fueled by liquid hydrogen and liquid oxygen, this burn by the newest and higher performing variant of the RL-10 engine powers Centaur to orbital velocity. During ascent, the SBIRS satellite is protected inside a 4-meter diameter payload fairing. At 4 minutes 34 seconds, once the vehicle has climbed above the densest part of Earth's atmosphere, the payload fairing is jettisoned. At 15 minutes 6 seconds, cutoff of the Centaur main engine, or MECO-1, occurs. 31 seconds later, EZ-3 is deployed. EZ-3 and EZ-4 are fully integrated flight systems attached to the aft end of the Centaur. Each of these systems contains a 12U canister containing small multi-manifest satellites sponsored by the United States Air Force Academy that will help in creating critical capabilities that support the warfighter. Following EZ-3 deployment, the Centaur performs a 180-degree roll and deploys EZ-4 at 16 minutes 25 seconds. At 31 minutes 6 seconds, the Centaur main engine is restarted. Following a nearly 3.5-minute burn, powered flight is complete, and the Centaur main engine shuts down. Centaur and the spacecraft will coast for the next 8 minutes. At 42 minutes 46 seconds, Centaur releases the 5th SBIRS GEO satellite for the United States Space Force, providing early missile warning detection for the United States.
ULA is using an Atlas V 421 rocket to launch SBIRS GEO 5. This is the 87th Atlas V launch and ULA's 144th mission. Built in Decatur, Alabama and Harlingen, Texas, Atlas V is comprised of a common core booster powered by an NPO Energomash RD-180 engine, equipped with 2 Aerojet Rocketdyne solid rocket boosters, and a Centaur second stage powered by an Aerojet Rocketdyne RL-10C11 engine and equipped with a 4-meter diameter payload fairing. Events began with lifting the 107-foot or 33-meter booster onto the mobile launch platform at the vertical integration facility. Then the SRBs were mated to the booster. After the satellite was encapsulated inside the payload fairing on April 30th, it was transported to the vertical integration facility on May 7th, where it was mated to the Atlas V rocket at Complex 41. An Atlas V launch countdown begins with moving the rocket from the VIF to the pad. 6 components are used for the 20-minute, 1/3 mile trip to the pad. The MLP, which weighs about 2 million pounds, supports the rocket and contains air conditioning, electrical, and commodities lines. Undercarriages bear the weight of the MLP and rocket. 2 rail cars lead the move. The payload van provides spacecraft communications. The ground van provides support for the rocket. At the rear of the convoy is an environmental control system providing air conditioning to the payload and rocket. Trackmobiles power the nearly 3 million pound convoy. The Atlas V rocket stands 194 feet, or about 59 meters tall, and weighs just under 1 million pounds, or nearly 431,000 kilograms, fully fueled. ULA's Atlas V is launching the 5th dedicated satellite in the space-based infrared system. Built by Lockheed Martin, this is the first launch of a satellite using the company's modernized LM-2100 combat bus, an enhanced space vehicle that provides even greater resiliency and cyber hardening against growing threats, as well as improved spacecraft power, propulsion, and electronics. SBIRS GEO 5 is equipped with powerful scanning and steering surveillance sensors to protect our nation 24/7. These infrared sensors collect data that allow the U.S. military to detect missile launches, support ballistic missile defense, expand technical intelligence gathering, and bolster situational awareness on the battlefield. Also riding on today's Atlas V are 2 multi-manifest satellite vehicles, EZ-3 and EZ-4, which contain 2 technology demonstration orbiters known as TDO-3 and 4. These satellites, sponsored by the Department of Astronautics at the U.S. Air Force Academy, will ultimately be used to create capabilities that assist the nation's warfighters in performing their critical missions. Led by the Mission Manifest Office, this multi-organizational design, analysis, manufacture, test, and integration effort was performed within just 9 months. Getting a rocket and satellite prepared for launch require a lot of work coming together at the right time. Mission Integration Systems Engineer Tim Pica tells us how it's done.
Primarily, my focus is on defining all of the interface requirements to take the payload and put it onto our Atlas rocket. That includes defining all of the hardware, environmental, launch site requirements, and then on the tail end of the mission, right around now, is where we're finishing all of the verifications tied to ensuring that we meet all of the requirements to get both SBIRS and Centaur to end of mission successfully. The work really starts about 2 or sometimes even more years before a launch, where we get a set of requirements from the payload customer, and then from there it's an ongoing process to work with both the payload manufacturer as well as the government teams to kind of make sure all of the requirements are defined for all those interfaces between our rocket and the payload. ULA does have a history of launching SBIRS missions. We've done 4 to date, starting back in 2011. What's unique about SBIRS 5 is that Lockheed Martin redesigned the satellite Specifically, certain thermally sensitive components are in new locations. In the case of SBIRS 5, we do consider it a short coast mission, meaning it's only about 43 minutes from the time we launch to the time we separate. So it did pose some unique challenges for us to ensure that we could keep all of those components on the satellite within their thermal constraints. With SBIRS, we do have the 2 additional CubeSats that we consider auxiliary payloads to the mission. So our primary goal is to get SBIRS where it needs to be successfully, but we also have in work with the auxiliary payload team, which is a different customer, to define their requirements and make sure we get those payloads where they need to be. One of the challenges with this is you need to make sure that the requirements for the secondary payloads don't induce extra risk onto the primary payload. So that really is the exact same process we go through with the primary payloads, but with the added step of ensuring that nothing we're going to do with the secondary payloads is going to increase risk to successfully completing the SBIRS mission.
The artwork on the payload fairing of today's rocket features a 5-sided pentagon to represent the 5th SBIRS GEO satellite. Additionally, an eagle, the mascot for SBIRS, is front and center in its claws to represent this missile warning mission. We also see 5 red beams emanating from the center star to represent the SBIRS infrared capability, as well as this, the 5th GEO satellite. Finally, the SBIRS motto, "Always Vigilant," is imprinted on the missile. We remain in the planned 15-minute hold as we continue toward liftoff. In a few moments, launch conductor Scott Barney will poll the launch team for the final go to pick up the countdown. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check for all Atlas vehicle systems, ground systems, spacecraft, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling.
LCS redline monitor.
Go.
Roger, step 150 is now verified.
Roger.
LDLC, net 1.
LDN1.
Here we are close, very close to our topping. Recommend extending the hold.
I copy.
LC switch
Please
will remain
extend
in
the
a
hold.
ready position.
Heard launch conductor Scott Barney recommended to the launch director that we extend our built-in hold for just a few minutes while the team monitors a propellant conditioning issue. So we will stand by and await an updated T0.
LC LOX 1.
Go, LOX 1.
Pogo suppressor charge is complete.
Roger. And LOX 1 LC, your status on step 850.
Atlas FLO2 at flight level.
Roger. And with that, all steps are complete prior to the status.
LC STD.
Go.
Spacecraft is configured for launch.
Roger. And RLM LC. Go ahead. I'll again verify red line monitor and event table in the correct configuration for terminal count.
Verified.
Roger. Okay, all personnel stand by for the status check. And we'll get a new T0.
With all the required activities prior to terminal count now reported complete, the team will choose a new T0 and we'll get moving here momentarily.
T0 of 1737.
1737 Zulu. Roger. RC, LC, note 1.
RC.
Please coordinate a new T0, 1737 Zulu.
1737 Zulu in work.
ALC, set the clock for a T0, 1737 Zulu.
Roger.
Copy.
LC, ALC.
Go.
Countdown clock has been set for a new T0 of 1737.
Roger.
L minus 9 minutes.
LC, RC, net 1.
Go, RC.
New T0 is approved.
Roger. Okay, all personnel, we have an approved T0 for 1737 Zulu. LC switch to the ready position. All steps are complete prior to the status check.
And as you just heard, the clocks are now set for our new T0 of 1737. The range is approved the new T0 and the team is now ready to proceed with countdown. Launch conductor Scott Barney will resume his activities and conduct the poll for terminal count in just over 1 minute.
L minus 8 minutes. L minus 7 minutes.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
HASGAS.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operations support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Red line monitor. Go. Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
You have permission to launch.
Proceeding with the count. ALC. Verify T0 is set for 1737 Zulu.
Verified.
Polling is complete. The ULA launch team and the Space Force mission director are go for launch. From T-minus 4 minutes until launch, you'll be listening to Scott Barney and his team performing the final steps in the countdown procedure. You'll hear the team call out that Atlas liquid oxygen topping has been secured, followed about a minute later by the call out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur liquid hydrogen and liquid oxygen topping activities. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, Atlas tanks will be verified to flight pressures, followed by a verification of Centaur tank pressures. A final status check of Atlas, Centaur, and SBIRS GEO 5 readiness is conducted at T-minus 25 seconds. At T-minus 3 seconds, the RD-180 engine will roar to life. After liftoff, you'll hear the voice of Patrick Moore providing launch vehicle Ascent data.
STD, this is LC. Please re-verify spacecraft remains configured for launch.
Verified.
Roger. All steps are complete prior to terminal count.
This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
On my mark, the time will be T-minus 4 minutes and counting. 3, 2, 1, mark. 3:55.
The countdown clock has resumed, and we are go for launch at 1:37 p.m. Eastern Time.
T-minus 3 minutes.
Securing LO2 stopping.
Atlas tanks to flight pressure.
2 minutes, 50 seconds.
FTS internal.
$159,
Vehicle internal.
$155,
Launch sequencer start.
$150,
Securing Centaur LH2.
Securing Centaur LO2.
$140,
Launch enabled.
$137,
FTS armed.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
120,
OCU's armed.
FCS count started.
110,
Vent valves locked.
T-minus 1 minute.
Rock, report range status.
range green. 40 seconds.
Stable at step 3.
$25.
Status check. Go Atlas. Go Centaur. Go SBIRS.
T minus 10, 9, 8, 7, 6, 5, 4, 3, Atlas ignition, 2, 1, and liftoff. Liftoff, the United Launch Alliance Atlas V rocket with the 5th space-based infrared system satellite for the United States Space Force.
Now 15 seconds into flight, PU's gone to closed loop control. Engine operating parameters continue to look good.
You are hearing the voice of Patrick Moore providing launch vehicle Ascent data.
Vehicle's now completing the pitch over program, body rates look good. Seeing good chamber pressure on both SRBs. And RD-180 now beginning the throttle bucket, engine response looks good. And now passing through Mach 1, Atlas V is now supersonic, and max Q, maximum dynamic pressure. Body rates continue to look good through the boost phase. Vehicle's now throttling back up slightly, engine response continues to look good. Chamber pressure on both SRBs continue to look good. Now passing 1 minute 10 seconds into flight. Atlas is now 10 miles in altitude, 4.5 miles downrange distance, traveling at 2,000 miles per hour. 1 minute 20 seconds into flight, standing by for SRB burnout shortly. Body rates continue to look good. Chamber pressure on the SRB is now tailing off. And we have burnout on both SRBs. Atlas will hold on to the SRBs for an additional 39 seconds before jettison. RD-180 is throttled back up to full thrust. Engine response looks good. Now passing 1 minute 50 seconds into flight. Body rates continue to look good throughout the boost phase. And the Atlas V now weighs 1/2 of its liftoff weight. And standing by for SRB jettison shortly. And we have good indication of separation of both SRBs. Now just under 2 minutes remaining in the booster phase of flight. Vehicle's gone to closed loop steering, seeing a slight correction in the body rates, now damping out nicely. RD-180 engine operating parameters continue to look good. RD-180 throttling down slightly now as expected. Two minutes 40 seconds into flight. Atlas is now 39 miles in altitude, 68 miles downrange distance, traveling at 5,400 miles per hour. And the Centaur reaction control system is now pressurizing the flight levels. System response looks good. Now coming up on 3 minutes into flight. RD-180 pump speeds and injector pressures continue to look good. Body rates continue to look good. Now about 1 minute remaining until booster engine cutoff. Pump speeds and injector pressures on the RD-180 continue to look good throughout the boost phase. Three minutes 30 seconds into flight. Atlas is now 56 miles in altitude, 160 miles downrange distance, traveling at 9,000 miles per hour. And RD-180 is now throttling to maintain a constant 5G acceleration limit. RD-180 responses look good. And Centaur's begun the boost phase chill down sequence. RD-180 now going to 4.6G throttle limiting, standing by for BECO. And we have BECO booster engine cutoff, standing by for stage set. And we have good indication of stage separation. We have pre-start on the RL-10, standing by for ignition. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good. And we have good indication of payload fairing jettison. This first burn of today's mission will last approximately 10 minutes, 30 seconds. RL-10 engine operating parameters look good. Body rates have damped out nicely from the startup transients. And the RCS system has begun the initial thruster firings for system thermal conditioning. Just over 5 minutes now remaining or 5 minutes now into flight. RL-10 chamber pressure looks good. Body rates continue.
This is Atlas Mission Control at T plus 5 minutes, 20 seconds. Patrick Moore just confirmed successful completion of the early phase of today's flight, and all systems continue to operate nominally. The mission is currently in the first Centaur engine burn. Our next event, Centaur main engine cutoff, will occur in approximately 10 minutes. Lockheed Martin builds the SBIRS satellites for the U.S. Space Force. Here's a video highlighting the power of these satellites.
It's 30 seconds into flight.
Last week, I had the opportunity to talk with Lockheed Martin's Melanie Young about the incredible capabilities SBIRS 5 brings to the constellation. Let's take a look at our conversation. Hey, Melanie, thanks for joining me this afternoon. Can you tell me more about what you do for the SBIRS program?
Yeah, thanks. I'm really excited to be here. I am a systems engineer for Lockheed Martin Space, and I've worked in the U.S. Space Force's Space-Based Infrared System, or SBIRS program, for 14 years.
Wow, that's awesome. For our audiences, can you tell us more about what SBIRS is and what SBIRS does?
Yeah, SBIRS is a critical system for the U.S. Space Force and for our national defense. It has a constellation of SBIRS satellites that continuously protect our nation and armed forces. The SBIRS satellites are equipped with scanning and steering surveillance sensors. They detect missile launches and support ballistic missile defense, expand technical intelligence gathering, and bolster our situational awareness on the battlefield. On the ground side, there's a ground station that receives and processes tons of SBIRS data. The SBIRS operators take that data and use it to make reports for defense and intelligence and civil applications. And SBIRS GEO 5 is the latest satellite to join the SBIRS constellation.
So the SBIRS program is very important to our national defense. You mentioned that this is SBIRS 5. We've launched 4 SBIRS birds in the past. Can you tell us what's different about SBIRS 5 compared to the previous satellites?
Yeah, we're very excited about SBIRS GEO 5. It's the most advanced and resilient SBIRS satellite that Lockheed Martin has built to date. It was built in about 5 years, and it's the first military space satellite built on our LM-2100 combat bus. So that is the version of Lockheed Martin's modernized modular LM-2100 space vehicle. It has greatly enhanced resiliency. That LM-2100 bus is an internally funded multi-year modernization initiative that has greater resiliency and cyber hardening, enhanced spacecraft power and propulsion and electronics. It's got a lot of processing and features as well, where we have common components that streamline manufacturing. And then it's got a flexible design so that you can put on future modernized sensor suites. So this is a huge step toward achieving, this resilient missile warning that is ultimately going to follow on in next-gen OPIR Block 0.
Wow, that sounds really important. That's really a significant upgrade compared to the previous birds that we've launched. I know for me, working in the industry, I find it really rewarding to participate in some of the launches that we do, both national defense and some of the science missions. What's it mean to you to work on the SBIRS program?
Yeah, I'm really proud to be a part of the SBIRS program, supporting our national defense. And SBIRS plays such an incredibly important role in protecting our country and our armed forces. And I'm really proud to be a part of this team.
Awesome. Well, hey, thanks for talking to me today. We recently received some sad news that a mutual teammate, Bill Levinson, had passed away. I know that Bill had a tremendous career with Lockheed Martin. He's also a longtime ULA employee when we formed ULA in 2006. He worked in our chief engineer's office, both in the major development as well as the chief engineer for the Delta program and then the Atlas program. He contributed in numerous ways to all of our programs.
Yeah, we thank Bill for his many years of service to the industry, and he will be missed.
Well, thanks again for joining me today, Melanie. It was really great speaking with you.
Yeah, thank you.
Once operational, the Space Delta IV team at Buckley Air Force Base in Colorado will control the SBIRS GEO 5 satellite. Let's take a look at a short video message.
Hi, I'm Captain Hannah Ritter.
And I'm Second Lieutenant Nicholas McDaniel.
We're here at Buckley Air Force Base, Space Delta IV. With faster, more accurate missile surveillance